everybody, we're back with another beautiful lesson about identities. So we're going to get a little bit deeper down the rabbit hole this time. So we're going to be using a couple extra identities in our proofs. So right here on the left hand side, I got 3 Pythagorean identities that are generally accepted to be true. And the first one, which is probably the one that you'll see most frequently, is that sine squared theta plus cos squared theta equals 1. Okay, now this one here can be rearranged in a couple of different ways. So that's where 2 and 3 come from. So if you take this and say you divide everything by cos squared theta, then you are going to get, just to show you an example, sine squared theta over cos squared theta. Now when we divide the second term by cos squared theta, that's going to just be 1. So you're going to have plus 1 equals 1 over cos squared theta. Now 1 over cos squared theta, well, that's secant squared theta. There's the plus 1 that we have, and sine squared theta over cos squared theta is tan squared theta. So that's where this identity comes from. Okay, so this one's proven to be true, and then we divided it by cos squared theta to get this second identity. And similarly, you can divide it by sine squared theta to get this third one down here. Now, these 3 identities are going to be on your formula sheet for grade 12 pre-calc, so you don't need to memorize them, but you do need to be aware of their existence. Again, the one that gets most frequently used is usually number 1 or some variation of it. So the 2 variations of it are simply derived from solving it for either sine squared or cos squared. Okay, so if you solve number 1 for sine squared, then you're going to get this identity. So this is a good one to memorize. I'm missing the thetas in here. So sine squared theta is the same thing as 1 minus cos squared theta. That just came from moving the cos squared theta over to this side, so that's why the sign changed. Very similarly, you can solve it for cos squared theta, and that's equal to 1 minus sine squared theta. So please keep that in mind. Those are super, super duper handy ones to have memorized. Definitely 100% for sure. Please do that. And I do believe that is going to be good. So we can move on to the next slide here. And we can go ahead and just start proving some identities. So we'll start with the one over here on the left-hand side. Now, again, the more of these that you do, the better you're going to get at them. Your best bet is to just start substituting things in where you can. So, for example, for cosecant theta, I know that that is 1 over sine. So when I go 1 over sine times cos squared, I'm going to get cos squared theta in the top divided by sine theta in the bottom, and then it just says plus sine theta, and it's going to write that over 1. So I need this to equal cosecant theta. Remember, cosecant theta is 1 over sine theta. Okay, so I'm looking at this and I'm sort of saying, well, maybe if I got a common denominator, that would help me out. So I'm going to multiply by a form of 1. So I'm going to multiply this fraction over here by sine theta over sine theta, which is going to give me sine squared theta over sine theta, and this one over here is not changing. There you go. So now you have a common denominator. So what you really have is you got cos squared theta plus sine squared theta, and that's all over sine theta. Well, we just learned that this identity here, that when you got cos squared theta plus sine squared theta, that's equal to 1. So we're going to substitute that in for 1. And now we have 1 over sine theta, which is equal to 1 over sine theta. So that one's done. Now, this one over here on this side, I changed it a little bit from what your note package says. So here it is. What you can do here is you can actually factor this, right? So this is looking a lot like a difference of squares, right? So if it is a power of 4, that's okay because these are still perfect squares. So when you factor that one, you're just going to get x squared minus y squared times x squared plus y squared. All right, so just use sine theta and cos theta for x and y instead. So you're going to have sine squared theta minus cos squared theta in one bracket. And then in the other bracket, you're going to have sine squared theta plus cos squared theta. Now again, we know that this is equal to 1. Okay, so you can go ahead and just kind of show that work. Remember, you don't want to do a million steps at once. Like, it's a proof, so you need to show exactly what's happening. So don't skip that step. Like, show that this is equal to 1 so that I can see that in the proof. So just remember that you got this identity here. It's super important. It gets used very frequently. So definitely memorize it. Now, trying to get over here, I need 2 co-squared thetas. So if I solve this thing for sine squared theta, I'm going to get 1 minus co-squared theta. So now I have an expression for sine squared, which I'm going to go ahead and substitute in. So there you have it. There's no more need to have the brackets because you can distribute the 1 in and you get here. So now just group your like terms and you have 1 minus 2 co-squared theta, and that's equal to the right hand side. So hooray! That's like the 5th time I've done this one. I've had a lot of issues with my microphone. Mostly I just forgot to plug it in and recorded a bunch of silence. So this one here, there's no obvious place to start. But you can usually do work on both sides sometimes. So on the right hand side, cosecant is 1 over sine theta times secant, which is 1 over cos theta. Okay, so that's a multiplication symbol. So I'm trying to get this from here. Cotangent's 1 over 10. So you probably want to plug in what the definition of tan is. Now, tan is sine over cos. So you got 1 over sine over cos, which means you're just going to do the reciprocal and you're going to get cos over sine theta. And again, tangent is sine theta over cos theta. Okay, now it's kind of like, well, you got 2 fractions that are being added and then these ones are being multiplied. So the only way to try to get what's on the right-hand side is to get a common denominator. So that common denominator, my LCD, is going to be sine theta cos theta, which is, as you can see, is what I have over here. So that's looking good. So I'm just going to multiply by a form of 1. So I'm going to multiply this by cos theta over cos theta. That's just 1. That's going to give me cos squared theta. I'm going to draw a big fraction line. Now, I already said that my common denominator is going to be sine theta over cos theta, so I'm just going to write that. So I just took care of this first part here. Okay, so cos theta, sine theta, there it is. The order doesn't matter. On this side, I'm going to multiply by sine theta over sine theta. Again, that's going to give me my common denominator of sine theta times cos theta. And then it's going to recopy the plus sign. Sine theta times sine theta is sine squared theta. Well, this is our famous identity that we just learned today. Cos squared theta plus sine theta is 1. So you have 1 over sine theta times cos theta. And that's equal to the right-hand side. So yay! You get another smiley face. And we are 1 slide closer to the end. And now this one, ooh, you know, this one's really ugly. Or at least it looks that way right off the hop. Again, not necessarily obvious where you're going to start. It doesn't, like, I know that cotangent to the power of 3 is 1 over 10 to the power of 3. So I'm going to keep that in mind. But I am seeing that I have a cotangent common to both pieces on the right-hand side. So what I'm going to do is I'm going to factor that out. And that's going to give me cosecant squared theta minus 1. Now, you don't need to memorize every single identity, but you need to know that you have identities for cosecant squared. Okay, so I'm trying to get a cotangent to the power of 3. So I'm just going to go back and look at what sort of identity I have for the cosecant squared, and it's right here. Now, I blotted it out, but this is 1 plus cotangent squared theta. Now, that's handy. So if I just subtract 1 from both sides, so there you have it. Now I have an identity for cotangent squared theta. It's cosecant squared minus 1. Well, that's exactly what I had over here. So this piece here in the brackets, that is cotangent squared theta times cotangent theta. So cotangent theta times cotangent squared theta is cotangent to the power of 3 theta. Yay! So that one is really easy. Of course, it could have been pretty ugly if I started doing weird stuff. So when you see one of those identities, it's very important that you utilize it. You might just want to straight up memorize them. I don't, but I sort of know that for the squareds, cosecant squared, secant squared, sine squared, cos squared, we have identities for that. So when you see them pop up in questions, you're going to want to go take a look at your list of what you got. Now, one last new strategy. So far, our general strategies has just been substituting in whatever we can for sine, cos, tan, all those things there. Sometimes you need to rationalize your denominator in order to solve. So you might not remember what that is. That's coming back from grade 11. So back in grade 11, we told you that if you had a square root in the bottom, you had to rationalize it by multiplying by a form of 1. When you multiply a square root by itself, it's going to go away, and now the square root's gone in the denominator. Sometimes you guys had denominators that were binomials that had a radical, and you learned that you could rationalize those by multiplying by the conjugate. Okay, so the conjugate of 1 minus square root 2 is 1 plus square root 2. So conjugate is just a fancy way of saying change the sign in the middle of a binomial to the opposite sign. That's the conjugate. Okay, so how do you know you're going to have to use the conjugate when you're solving an identity? Well, it's not really a tried and tested way, but in general, if it comes up on the exam, as it doesn't always, but if it does, it's going to happen with a binomial denominator. So if you see a binomial denominator that has like a 1 plus and then some trig function, it might be doing the conjugate. I don't see an easy way to do this question. Okay, so on the right-hand side, I sort of have this 1 minus sine theta, and then I have divided by cotangent. And then over here, I'm not even anywhere near, right? Like a 1 plus sine theta in the bottom. Like, how am I gonna get to the right-hand side? So the answer might be, we'll try doing the conjugate. So give yourself some room. Recopy the first fraction. Okay, and multiply by the conjugate. So the conjugate of 1 plus sine theta will just be 1 minus sine theta. So the only thing is you're just changing the sign, right? It needs to be a form of 1, so just go the same thing in the numerator and denominator. Now don't forget your brackets. If it's a binomial or bigger, good idea to have brackets so you don't forget the distributive property. So take a step back for a moment. I have this 1 minus sine theta right here. So that's good news. It's starting to look a bit more similar. Down here in the bottom, I'll show you some magic's going to happen. So for now, I'm going to leave this alone. I don't want to distribute this into the brackets because it's going to mess up my 1 minus sine theta. And that's just my experience doing a lot of questions telling me that. So if you're seeing a piece of what you're trying to get show up, maybe try not to mess it up if possible. Okay. So in the numerator, I'm just going to keep cos theta, sine theta. I'll keep some brackets around it, whatever. Keep that all. That's not changing. It's in the denominator that some magic is going to happen when you multiply a number by its conjugate. So you're going to get 1 times 1, which is 1. Then you're going to get 1 times negative sine theta, which gives you negative sine theta, and then positive sine theta times 1, which gives you positive sine theta, and then sine theta times negative sine theta, which gives you negative sine squared theta. So these two middle terms cancel out to 0, right? You got a positive 1 and a negative 1, they cancel out. So you have 1 minus sine squared theta. That's one of our identities, right? That is cos squared theta, right? If you solve this identity, right? And this one, you have to memorize this one. There's no way around it. It gets used so frequently. So sine squared theta is simply just moving this bad boy over here. Did I make a mistake somewhere? Nah, I didn't. So if you move, but I did sort of make a mistake over here. If you move the sine squared theta over here, now you have cos squared theta equals 1 minus sine squared theta. Why do we care? Well, we have 1 minus sine squared theta in the bottom. So I can write cos squared theta. So I'm going to do that. So cos theta, sine theta, not changing that. These are so annoying. Remember, you got to show every step. So you can't skip any of this. So recopy all of that and just write cos squared theta. Now, why do we care so much about that? Well, basically what we got over here is we got 1 over cotangent theta times 1 minus sine theta over 1. Okay, so I'm basically trying to get this cotangent theta. So cotangent theta is 1 over tan theta. Okay, so you got 1 over 1 over tan theta. So basically, you just have tan theta times 1 minus sine theta, right? Just do the reciprocal. So can I get a tan theta here? And I'm thinking I can because I got a sine theta. And look, everything's being multiplied in the top, so you can cancel one of your cos thetas down here with this cos theta. So now you just have sine theta over cos theta times 1 minus sine theta over 1. Now this is tan. So I'm feeling lazy and I don't want to rewrite this. So I'm just going to over here, I'm just going to write sine theta cos theta for tan, and then 1 minus sine theta. You have to clearly show exactly how they're equal to each other. So stopping here would not have been enough. You need to show that you realize tan theta is this, which is the same as that. Woo! So that one was really ugly. I mean, they don't get any harder than that on the exam. Generally on the exam, I find that they're usually a bit easier. So just to wrap up this whole topic, we're just about done. We're on to the last one. I'm going to show you another trig equation. So we have trig equations still that show up. You cannot solve one of these if you have two different trig functions inside an equation. Okay, so sometimes you got to use the new identities that you learned today. So I know that cos squared theta is 1 minus sine squared theta. Now it's not theta, it's x in this case. So don't change the variable or you'll lose half a mark. So there we are. And now I can distribute this into the brackets. I'm just going to do the order right now. So I'm going to get negative 2 sine squared x. And then I get a plus 2, which I'm going to recopy this middle term first. So I get a negative 3 sine x. And then there's my plus 2, and it's equal to 0. Okay. So I'm going to be having to factor this. There is one last thing I'm going to do before I suggest you pause the video and factor it. I can divide everything on this side by negative 1. Okay, so if I divide everything on this side by negative 1, all the signs are going to flip. So this one here is going to become a negative, and 0 divided by negative 1 is still just 0. So go ahead. I'm not here to teach you decomposition. You're looking for two numbers that multiply to negative 4. But add up to positive 3. So pause the video, do your decomposition, and I'll show you my answer in a second. Okay. Once you do all the factoring, you're going to get 2 sine x minus 1 times sine x plus 2. That's equal to 0. Now I use the zero product property to solve this bad boy up. To get sine x plus 2 equals 0. And you get sine x equals negative 2. Now, you should get alarm bells going off right now. That does not exist. So D and E does not exist, right? Sine x has to be between negative 1 and 1 inclusive. So that's just simply out of bounds. So no solutions on this side. Over here on this side, this is looking more promising when you set it equal to 0. So you're going to get sine x equals a half. So you can go ahead, find your reference angle. So these are the ones you memorize. It's an exact value. So your y value is a half at pi over 6. Now look at the domain they're getting us to solve this over. So they want us to solve it from pi over 2 to 2 pi, which means they're cutting out quadrant 1. So sine is positive in quadrant 1. So this would have been one of our solutions, but it got tossed as the domain. The other place sine is positive in quadrant 2. So you can draw your sketch, and you're looking for the rotation. How far is it from here to here? So it's pi minus pi over 6, which gives you 5 pi over 6, which is a value you can memorize or calculate the way I do it. So there you have it. That's all done. What a beautiful day. You can now do 7.4. We're so happy for you. It was such a pleasure having you guys again. And good luck doing those exercises. If you have any problems, give me an email or a shout out. We'll see you next time. Bye-bye. Bye-bye.